So are you able to see the whiteboard?
Yes, sir.
Okay, good. Let us start. So now we'll be doing second Laplace equation. Okay, so let us start with something called definition of a second order linear elliptic equation. Linear elliptic equations. Okay. So what is the meaning of a second order? Do you know what is the meaning of a second order? What is the meaning of second order? The highest order derivative involved in the partial differential equation is second order. You know that. Second order. Elliptic, linear, you know what is the meaning of a linear. This you don't know, no? Elliptic equation. So I will formally define what is the elliptic equation, and then we will start Laplace equation. Okay. So the general form is the general form of second order equation is like this. We call an equation is said to be a second order if this is the form 1 to n. I will come to that. Aij dou to u by dou xi dou xj. This is the second order derivative involved, plus the lower order derivative del u by del xi. Of course, I equal to 1 to n plus cx, a function, into u, a function, equal to fx. This is known as the second order equation. Okay, this is the general form of a second order. This is because why is a second order, Rahul? This is the second order term. Second order. This is the first order term, and this is the zeroth order term, or the zeroth order term. Okay, so you, of course, u is an unknown. You want to solve for given f. This is the PDE. You know what is the PDE, and what is Aij of x? Can anyone tell me what is the meaning of this summation Aij? This one, can you tell me what is d2u by del xi del xj for 1 less than equal to I j less than equal to. So this is a matrix. What is called matrix? What matrix is this is called? This is called a Hessian matrix. You know what is all possible, all second order derivative x1 x2. You know how to write down the matrix. So this is a matrix. So I multiply with another matrix Aij with the same ij equal to 1. Okay, that is the meaning of I, and you know what is the meaning of this. So I product of two matrix, Aij matrix, and now what is this Aij? This is very important. What is this coefficient? These are called the coefficient. This is a coefficient vector. This is a coefficient function, and this is a coefficient matrix. Okay. What is this coefficient matrix? That is what, because until now I have not defined what is meaning. What do you mean by the elliptic equation? So let us have some assumption of Aij matrix. Okay, the matrix which is the coefficient of the highest order derivative, that is del 2y by del xi del x, the second order derivative. Okay, what is that matrix? Where now I prescribe what are the conditions on the Aij matrix. So Aij matrix is symmetric. What is the meaning of symmetric? You know, symmetric. Now we will define what do you mean by elliptic equation. Okay, we call the above equation, that means the previous equation, the above equation is elliptic if this happens. Ij equal to 1 to n, the matrix Aij, the xi I xi j equals not equal to 0 for all xi 1 xi 2 nth vector for all xi. Did you understand what is the meaning of this? Aij xi I xi j not equal to 0 or summation ij equal to 1 to n. Did you understand what is this? This is nothing but, you have definitely come across with this. This is what is the meaning? What is this? Aij is a matrix, n by n matrix. Xi is a vector in n-dimensional vector xi. This is nothing but this multiplication. You know this. Xi n, the matrix Aijx, and the vector xi1. Sometimes it is written as A xi psi. What is called? What is called? AXX. What is this called? You remember what is this name? Quadratic form associated with the. This is the quadratic form. Quadratic form associated with the matrix A. Okay. So this is xi I xi is nothing but this is the xi1 xi2 up to the n vector Aij matrix. This is the meaning of xi I xi j Aij into xi I xi j. So this Aij, this is quadratic form is never equal to 0 for all xi in Ra. Then we called, so just come again start. So this is a second order elliptic equations. You understand this is second order elliptic equation. This is sorry, it's a second order linear equation. Now we call a new term we have introduced what is called elliptic. The differential equation is said to be second order differential equation is said to be elliptic if these matrix Aij is symmetric and it is what is called non-negative, what is called non-zero, and having a non-zero quadratic and the quadratic form. Is that clear? That is A xi xi is not equal to 0. Is that clear, all of you? Hello, is that clear to all of you? Yes or no? Manish, Kritika, Anshu, Govind, Ankit, Atharv, Shammi.
Yes, sir.
Clear? You have come across this term in this type of thing in linear algebra course, right? Am I right? Okay. So this is a quadratic form associated with the matrix A that is not equal to 0. That's then A is said to be an then the equation is this second order elliptic. This second order equation is said to be an elliptic. Okay. Now let A xi xi is not equal. So let us see what in terms of the eigenvalue it means. Suppose it's a symmetric matrix, so we can talk about the real eigenvalue. So lambda is an eigenvalue of Aij X matrix with eigenvector, let lambda with eigenvector xi. Then you know what is the definition of eigenvector? What is called if lambda is an eigenvalue of Aij matrix. This is the matrix A with eigenvector xi. What does it mean? Huh? What is the expression?
Is I equal to
Xi is equal to lambda xi. Now you just inner product with xi. That is lambda xi square. And what is this? Huh? Summation Aij x xi I xi j. That is lambda xi square. So what can you say about the if this is not equal to 0? Because I assume that Aij so Aij matrix that Aij matrix satisfy the elliptic condition. This is elliptic. We assume that we call the above equation elliptic if this coefficient matrix is not equal to 0. So this imply lambda xi square is not equal to 0. What can you conclude about the eigenvalue? If lambda is an eigenvalue of the matrix Aij, then what can you conclude about the eigenvalue? If Aij is a elliptic, so it satisfies the elliptic. If the equation is elliptic, then the Aij, let's say lambda is an eigenvalue of Aij with the eigenvector lambda, then this happens. So what can you conclude about the eigenvalue lambda?
should be non-zero.
Exactly. So therefore, if the equation, because eigenvector means non-zero eigen, of course we call xi is not equal to 0, right? It's an eigenvector. So lambda xi square is not equal to 0. That means therefore if the equation is elliptic, then all the eigenvalues are either positive or negative. Really, we already know because they're symmetric. Negative. Okay? Is that clear? So without loss of generality, we assume. So without loss of generality, we may assume it's positive. Okay? We assume summation ij equal to 1 to n aij xi I xi j is positive for all xi not equal to 0. Then consider this function. Consider this function. What is the function? Xi going to a xi xi. The inner product a xi xi. That means summation aij xi I xi j. So define a function f xi is given by summation aij is a fixed matrix xi I xi j. Is this a continuous function? Yes or no? Is this a continuous function? The x going to txx. Is this a continuous function? Is this a continuous function? What happened? At least answer yes or no. Hello? Can you hear me? Atharva Shammi, can you hear me? Hello?
Hello. Yes.
Is this a continuous function?
Yes. Like maybe each component, if you consider each component, then kind of a polynomial in that component. So continuous in.
Straightforward. X going to the txx. Is this a continuous function or not? Huh? Okay, check. Check. F is a continuous function. Okay, this please check. F is a continuous function. Okay. Now consider this set. The set xi belongs to Rn such that mod xi equal to 1. What is this set? How it looks? What is this set? How it looks? This is a circle. Mod xi equal to 1. Okay. Is this a compact set or not? Is this a compact set?
Yes, sir.
Yes, sir.
The set mod xi equal to 1 is the comp. So since we are working in Rn, so now I hope you have understand. You are learning this function analysis. You know that unit ball is compact if and only if it's a finite dimension. So Rn is a finite dimensional, so unit ball is compact. So mod xi equal to 1 is a compact set. Is a compact set. And now you consider the function f, but which we define from a xi xi at mod xi equal to 1. What can you say about that function? So if I am defining from this set, xi belongs to Rn such that mod xi equal to 1. From this side, you know what is R. So it's a compact set. So what can I say about the function f? F is a continuous function of a compact set. So what I can say about f?
It's bounded.
Yes. So what this imply? There exists a constant m and capital M positive such that summation aij so of course is depend on x because I have prescribed x for each x xi I xi j. So I consider the function for let's say fx. What is this fx? Fx at xi for fixed x. This is aijx xi I xi. Okay, for fixed x, this is a continuous function, and on a compactor, so it will attain is, you know what is the meaning of that. Mx greater than equal to small mx. Okay, for all xi with mod xi equal to 1. Okay, now so what we have obtained, that summation aij x by just using the ellipticity condition, less than equal to mx greater than equal to small m of x for all mod xi equal to 1. Now I claim that these imply mx, of course this is positive, less than summation aijx xi I xi j is greater than capital Mx for all xi not equal to 0. So how I come from this step to this step? So for mod xi is a compact set, so I have this inequality. F is a continuous function. For each x, I have this inequality. As you said, f should be bounded. Now you tell me how I come from this step to, for now this mod xi, not instead of mod xi equal to 1, I am taking for all mod xi not equal to 0, I have this inequality. How I come to this? I came to this. Oh, sorry. With mod xi square, mod xi square. Sorry. How I came to this inequality? Huh? You just define eta equal to xi by mod xi. So mod eta equal to 1. Agreed? So on this set summation aij eta I eta j is this. Clear? Is that clear? Now you write down eta j. This is summation aij xi I xi j mx into mod xi square, because eta I is mod xi square, mx into mod xi square. Clear? Just scaling with mod xi. Here use this factor. Okay, then I got this inequality. Okay, so for each x in omega, if the equation, that second order elliptic equation elliptic, we have this condition aijx xi I xi j is less than m of x mod xi square m of x mod xi square. That's it. Okay, for all mod xi not equal to 0. Now I will define a new concept known as uniformly elliptic. We say now, until now we have defined what is an elliptic. Elliptic means summation aij xi I xi j not equal to 0. Just from using this definition, we can conclude that we have this. That is for each x xi I xi j, xi I is greater than mx into xi square. Just using this, that if that equation is an elliptic. Now I am defining a new concept. We say that the above equation, that the same equation, LU, that equation, the above equation is uniformly elliptic. Now we call a new term uniformly elliptic. Until now we have defined what is elliptic. Now I am try to define a new concept known as uniformly elliptic. If there exists a m positive, a uniform m positive, it does not depend on the point x, such that summation ij equal to 1 to n aij xi x xi I xi j is not equal to 0 is the ellipticity condition. Now we say that it's a uniformly elliptic. That means I greater than equal to m into xi square for all xi not equal to 0 and for all x. Is that clear? See, Here I often using ellipticity, I have obtained aijx xi is greater than mx into xi square. So this bound depends on x, right? This bound depend on x, because for each x I define a continuous function fx xi by a xi, and we look at the set mod xi equal to 1 since it's a compact set. So for each x f we will have a, so this is ax, we will have a condition m, and for again using scaling, as I say, eta by mod xi by mod xi, we obtain aijx xi is less than mx xi square capital. Now, but it depends on x. Now we call an equation is called uniformly elliptic if there exists a uniform m which does not depends on m, such that these lower bound holds. Thus aij xi is greater than m times mod xi square. Thus this m does not depend on the point x. Is that clear? This is very important, you should understand this. Is that clear to all of you? What is the difference between uniform elliptic condition and only elliptic? Only elliptic means xi not equal to 0. But uniformly elliptic means it is bounded away from 0 by m into mod xi square. Is that clear to all of you?
Yes.
Okay. Good. So let us give.
Sir.
Yes.
Sir, we don't have an upper bound here, capital M.
Yeah, a capital the same. We are not bothered about the. Okay. Clear? This comes free from ellipticity, not found. Uniform ellipticity only gives you the lower bound. Clear?
Yes, sir. Yes, sir.
Okay. Thank you. So let us do some example. Because the Laplace equation, we will be doing the Laplace. So what we have studied till now, we have studied what is the definition of elliptic equation, what is the definition of general form of a second order elliptic equation, and then we define what is uniformly elliptic, and we see what is the eigenvalue and all those things. So Laplace equation, this is a famous equation. Summation I equal to 1 to n dou to u by dou xi square to f. Now you tell me. So this is the equation. So you are, so why what I said, this is we said that a second order elliptic equation is the form aijx dou to u by dou xi dou xj plus bix dou u by dou xi plus cxu equal to f. This is ij equal to 1 to n, I equal to 1 to n. Now you just try to have a similarity between this Laplace equation. So you tell me what is bi in the Laplace equation? What is bi in the Laplace equation? Huh?
0.
Excellent. This is bix is 0 for all I equal to 1 to n. What is cx in the Laplace equation?
0.
Very good, cx. So both gone. Now you tell me what is aij in the Laplace equation? Huh?
1 if I equal to j and 0 if I not equal to j.
Excellent. This is delta ij. That means this is a matrix 1, 1, 1, all the diagonal entry 1 and 0 otherwise. Is that clear? For the Laplace equation, for the Laplace equation, aij matrix is delta ij. How it looks like? 1, 1, 1, dot, 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 1 is in the diagonal elements. So this is 1 if I equal to j and 0 if I not equal. This is the matrix. Okay. So this is the matrix for the Laplace equation, and of course bix, the vector bi, the vector b is 0 and cx is 0. Now you tell me whether this is an elliptic equation. Whether this is an elliptic equation. Yes or no?
Yes, yes, sir.
Because aij xi I xi j. What is this? For delta, so this is summation delta ij xi I xi j. What is this? What is this?
Xi I whole square summation.
Summation xi I. That is mod xi square, right? That is mod xi square. Yes or no?
Yes.
This is not equal to 0 for xi not equal to 0. Now you tell me, is it uniformly elliptic? Is it uniformly elliptic? Huh? Is it uniformly? Just again think.
Yes, sir.
Aij xi I xi j. That is summation delta ij xi I xi j. This is mod xi square. Is this uniformly elliptic? Yes or no?
Yes, sir.
What is small m?
1.
Yes, very good. This is m into mod xi square equal to 1. So Laplace equal to f is Laplace operator is uniformly elliptic, second order equation. Clear? Now one more example. Second example. You just check. This is you check. I equal to 1 to n x del square u by, let's say, del x1 square. Is it elliptic? Is elliptic if xi is positive for all I. Is not elliptic in Rn. Is not elliptic in Rn. Okay, just check. Please check. One line. Okay. Clear? So now onwards, we shall study in a great depth. We shall study in details about Laplacian u equal to f. First case, I will study Laplacian u equal to 0. It's a beautiful equation. There are many physical, geometric, many things this equation arises. The above equation arises. Okay? One of the fundamental equation in the mathematics. Laplacian u equal to 0. One of the most fundamental equation in mathematics. Okay? Laplacian u equal to 0. Okay? So this is also the steady state equation for the heat and all many to model some numerous physical. Most of them is the heat flow. Put a heat in the system, how the heat flows along the system and all those things can be governed by this equation Laplacian equal to 0. Okay, so of course in the steady state also there are many geometry. If you study some differential geometry, then you will see this type of equation arises. Laplacian u equal to 0. Okay, now we will be studying in a great depth what are the properties of Laplacian u equal to 0. Okay, is that clear? Is that clear?
Yes.
Do you have any questions? You can ask me. Now I will start. This is known as harmonic functions. Harmonic functions. Okay. So definition. Let omega be an open set in Rn. It might be Rn also, the full set Rn. Okay. We say that u a C2 function. Okay, you know what is a C2 function. That means what is a C2 function? What is a C2 function? What is a C2 function?
Having continuous second order
Yeah,
derivatives.
excellent. Yes, U is a C2 is a harmonic function. Harmonic function if Laplacian U at each point x equal to 0 for all x in omega. Okay, so omega can be Rn also. Let omega be an open set in Rn. Of course, why you say openness? Because we are to define some derivative and all those things, so we need openness. Open set in Rn, we say that U(C2) function is called an harmonic function if Laplacian U at the point x equal to 0 for all x. Is that clear? Example, can you give me an immediate example? Example of a harmonic function. Give me.
Constant function.
Excellent. Ux equal to C. Constant. How is this function? A linear type function? AIXI. Is that a harmonic function? Yes, no? Yes, or no?
Yes.
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 Okay. So you can cook up example, anything. You can cook up example. So Laplacian. Now we will be studying. Now we shall study the properties, the analytic properties. We shall study analytic properties of very interesting harmonic functions. Okay, study analytic properties of harmonic function. So now we shall study analytic properties of harmonic functions. Okay, see how beautiful. So have you studied some complex analysis? Do you know anything complex analysis? Yes or no? Manish, Kritika, Anshu, Govind, Ankit,
Yes, sir.
Athar, they have studied some complex analysis, right? So let's see how is this theorem reminds you something. First theorem we will be doing in Laplace equation. There are many theorems we will do. This is called mean value. This is one of the fundamental theorem in Laplace equation. Mean value property. The fundamental theorem. Let U is a C2 omega be harmonic. You know what is the meaning of harmonic? That means for each point x in omega, Laplacian of U equal to 0 is harmonic. Then, so beautiful properties. Let's see. X belongs to omega and for any R positive such that Pxr is contained in omega, we have 1 over. What is the meaning of this? Mod. What is the meaning?
Measure.
Yeah, measure of Bxr. Okay, so omega is an open set in Rn. Okay, we integrate with respect to integrate over the domain Bxr uy dy. This is nothing but if you integrate over the boundary of the ball. Okay, del Bxr sigma. You know what is a sigma? What is sigma? What is sigma? I have said to you this many times. It's a boundary measure of, because the Rn measure of the boundary of a ball is 0. So you have to take a one measure less than, right? This is a boundary measure, surface measure. Surface measure. So if U is a harmonic function, then the integral, the average, the 1 by Bxr integral Bxr uy is same as if you integrate on the boundary of the ball. Okay, uy dy. And in that case, this is equal to U as x. See, so if U is a harmonic function, and what is the meaning of this? You take a open set omega. Okay, it's not boundary anything. You take x for each x. You have an x. You have an r because omega is an open set. So for each x, we have a ball of radius r, which is sits strictly inside omega, right? So this is your r. Okay. So you evaluate the function, a harmonic function u at the point x, which is equal to, you can write ux equal to in terms of the integral on the boundary, the u integral over the boundary of the ball, and which is again is equal to the integral over the whole ball with a measure 1 by divided of the measure. So now you tell me, in complex analysis, which theorem is analogous to this? Something, some analogous property of complex analysis. Which one? So the function, if u is harmonic, then at each point, the evaluation of if you evaluate u at the point x, which is equal to, you can write directly, which is equal to the integration over u over the ball boundary of the ball, which is again equal to the integration over the whole ball, not the boundary, whole ball. This type of thing, where you have studied in the complex analysis?
Yes, the same, like in terms of contour
So which
integrals.
what is called? What is this called?
Like also,
Huh?
like it's
Cauchy integral formula. You remember? Cauchy integral 1 by 2 pi I integral mod xi equal to this f xi by mod of z, that kind of thing. Of course, it is not exactly like that, but very similar to that. Is that right? Cauchy integral formula. If the function is analytic, then f of xi, you can write 1 by 2 pi I integral mod xi equal to r f of eta by mod xi by xi minus eta d xi, right? Is that clear? Anything reminds you? Huh? It's not exactly. I'm not saying that is exactly, but very similar to that, right? You can write the any analytic function can be written as the form of integral, right? The Cauchy integral, right? Yes or no?
Yes, sir.
Very similar to that, right? See how beautiful this theorem is. Any function you can directly write ux in terms of the integral over the ball or the integral over the surface of the ball or the circle, what is called circle, right? The proof is not that easy. Okay, we have to prove. Please ask me whenever if you have any doubt in the proof, because this is one of the fundamental step. I will be using some fundamental, very important steps in the proof. Okay, because then there's this type of proof I will do every time in the course. Okay, so for this proof I will be going very slow so that you can ask me question. Okay, is that clear to all of you?
Yes.
Good. So what is given? You just think what is given. Given, just be careful in this proof. Ux equal to 0 for all x in omega. Now you have a set omega. You fix some any x where such that bx you sit inside. So what is that? Fix x belongs to omega. Define for r positive such that you can take any r for such that bxr is sitting inside omega. Okay. It doesn't matter. Whatever r you take such that bxr, it will be having the same ux. Okay, that's the theorem. Now define a function phi r, because I have fixed x. Okay, you have fixed x in omega. Now you define a fixed phi r. It's a define. Okay, 1 by sigma means the surface measure, that is one dimensional measure less than Rn. So it is an n minus 1 dimensional measure. Del b xr. Okay, integral. D sigma 1. You know what is the sigma meaning. So I have taken this, I define. So for fixed x, I have fixed x in the domain, and I define for r, I define this. R is a function, right? Now I have not fixed r because we will take for all r, for all those r, this phi is defined for all those r such that bxr is contained in omega. Is that clear? But then we can define this. Is that clear? I am taking, though phi is a function, what is the domain of this function? The domain of the function is 0 to infinity. That means for all those r for which bxr is contained in omega, because you cannot take this very big r which is outside. So you have to take those r for which bxr is contained in omega. Is that clear? The definition? I have fixed term x and we are taking all possible r such that this bxr is contained. Now with this r I define a new function such that r is varying now. For a fixed x, uy dy, it will be depends on r. This whole integral is depend on r. Is that clear or not? Yes or no?
Yes.
Now I am writing this is equal to 1 by, just look at those steps, sigma del b 0 r del b 0 r. What I should write? Interior. What I should write?
I minus x plus x.
Is that clear? X, this is the boundary x r. I have just translate to some 0 and I just take the integral over the boundary. Is that clear? I have just taken x to 0. So for that I have to do y plus x. Is that clear? And the measure should be same, because you know del b x r is equal to del b 0 r, because this sigma is a n minus 1 dimensional Lebesgue measure and we know that the Lebesgue measure is translation invariant. Is that clear? The Lebesgue measure
Yes,
of a
sir.
surface of the ball is equal to the Lebesgue measure. Okay, good. So what I have now, PR is 1 by sigma del B 0R. So this is clear. Please ask me question if you are not clear to this. Now I substitute y is equal to y, x is a fixed, I have y equal to rz. So what will be d sigma y? Huh? R is a scaling. R is a
R
fixed.
is to n
R
minus 1.
raised to the
Yes.
power?
N minus 1.
Exactly. Okay. And then Z is y by R. So mod Z is mod y by R. So what is mod y? Y is in 0R. What is the meaning of mod y then? Huh? Y is in the surface of the ball. What is the mod y? That means
R.
clear. So now the integral will be equal to just the above integral. If I with this substitution, the what will be the above integral? 1 by क्या होगा? Y is your RZ, r to the power n minus 1 d sigma z. Now where is this z? Integral over, earlier it was del b 0 r. Now what is your z? Del b
0.
0, 1. 0, 1.
clear? Is that clear?
Yes.
Oh, sorry. What will be this? Something is there missing. This is integral over del b 01. So 1 by del b 01 is, what is the relation between sigma del b 0 r to sigma del b 01? What is the relation? Equal to, there is some factor missing. What is that? What is that? Scaling from R to
R is yes, sir.
yes. Scaling, man. It's just a scaling. Okay? Okay, so this will be R to the power n minus 1. So these R to the power n minus 1 cancels out. Okay? So you get phi R is 1 by sigma del B 0 1 del B 0 1 u of x plus rz d sigma z. Clear? Clear है? Is that clear? Yes or no?
Yes, sir.
Okay, good. Now what I will do, I will derivative. क्या होगा derivative? अगर मैं if I do derivative, this does not depend on the derivative r. The integral does not depend on r. Only the function depends on r. So what will be this? Huh? If you use the fundamental theorem, it is del v derivative over this. So what will be this? Tell me. If I derivative this function with respect to r, what will be this? Chain rule. U is a Rn, so gradient of u
Z.
at the point Rz, inner product with z. Very good. Okay, clear? Now what you will do? Now you again put x plus rz. It's a very interesting and very important theorem. Y. Okay, substitute. Then your z is y minus x by r. Okay, so d sigma z is 1 by r to the power n minus 1 d sigma x is a fix, so d sigma y. Okay, if I do this substitution, so d sigma this will be, if I do this substitution, this will be phi prime of r, this will be 1 by, just think what z is now. What is mod z? This is mod y minus x by r. This is a, what is this? What is this?
1.
1. So if I now if I want to write in terms of y minus x, so z will, this is a, what is this? Del b 0, sorry, del b x radius is 1, right? Huh? Y minus x? If in terms of y, right? If z is mod z equal to 1, as you said, now I am saying that where the y will lie now? Y is x plus rz. So where the y is lie now? Huh? Where will be the y lies?
On the surface,
Surface of radius
1.
radius 1 and center
X.
yes, good. So that will be del b x radius is 1, right? 1. This is del b x1 1. This is gradient of uy y minus x by r. This will be sorry, this will be r. Sorry, this will be r and d sigma y. Is that clear? Into, sorry, into r to the power n minus 1. Is that clear? Because dz, you just write down dz equal to 1 by r to the power n minus 1 d sigma y. Okay, clear? Now you write down y. So now the radius is r. So now you can write x y minus x is equal to rz. You take modulus of this. This is r because mod z is 1. So y lies in, so y is in bx of r. Is that clear? Y is in bxr. Is that clear? Yes or no? With this
Yes.
equation, y I have put here. So this will be mod y minus x equal to rz. Now you take the modulus. That means mod z equal to 1. So this is r. So y is like sorry del. So y lies in del b xr. Is that clear? Yes or no?
Yes.
Clear? And 1 by r to the power n minus 1 is hanging around. So you can take it out. So this will be r to the power n minus 1 del b x1. Right? That is sigma del b xr scaling. Del b xr gradient of uy. Now you have to tell me what is this. What is this? Now you have to think for 2-3 minutes. What I can write from here? This equation. Think about it and tell me. This is the big step and the final step. Just think. This is the boundary of the ball. This is a gradient. What is this? Some vector, right? Pi minus x by r. What is type of vector is this? Now you can think. I give you a hint.
Unit outward normal.
Unit outward normal. Exactly. This is a unit outward normal of a ball. Now you tell me from here what I can write. This equation is equal to. This integration is equal to. Just think. Stokes theorem, divergence theorem, whatever called, Gauss theorem, Gauss divergence, Gauss-Stokes theorem, Green's theorem. There are many names, or it is actually integration by parts. I will write down. Wait. This is equal to, this is the integration over the ball. This is a unit normal of the ball. This is a gradient. If you want to go to bxr, this is Laplacian u dc, not d. dy. Which theorem? From this step to this step, what I have used? This I have used what is called. This is I have used integration by parts. You cannot, so just recall. Gauss-Green theorem. Omega be a blah blah blah. Omega be a bounded open set. Smooth, of course, smooth. Okay. Omega del u by del xi dx is del omega u nu y d sigma. Example, you understand, right? This is just integration 1. So you want to take the derivative over 1. So it is 0. So only the boundary terms comes. This is just an application of integration by parts. Example, if you want to do this in the ball, let's say bx naught r, a particular example, del u by del xi dx. This is del b x naught r. U is there. What is the unit normal? Xi minus x naught I. Ith component, because I have taken I. R d sigma. Now here I have used. What have I used? We have del b xr. Gradient of u at y minus x by r, the inner product, d sigma y, right? This is equal to pxr divergent of gradient u d sigma y. If you just take what is the divergence of the gradient u, this is bxr Laplacian u, sorry, not d sigma dy. Is that clear? Is that clear? What is the divergent? This I can write as bxr. If you don't like this, summation dou by dou xi dou u by dou xi. Okay? Now apply dou by dou x. This is your v function. Let's say 1. So summation bxr, you take the summation out, dou by dou xi v. Just use this theorem. It's your v. That is v into nu I summation. Got it? Did you get this?
Yes, sir.
Yes.
Get it? So we have this. This is a beautiful application of Stokes. I used to call divergence theorem, or you call Gauss theorem, you call Green's theorem. But the main thing is this is just a integration by parts. Okay? So this happens this. Now what I can say, what is Laplacian of u?
0.
Because u is given to be a harmonic function. So what I have obtained? What I have obtained?
P dash of r is 0. So P must be constant.
No, yes, phi prime. Just a minute. Phi prime of r equal to 0 for all those r such that for a fixed x, bxr is contained in omega. These are domain. Okay, this imply phi is constant. Agreed? Yes or no? This imply, yes. Because this is a constant, I can write phi r as limit, because for all r positive it is defined. Phi is a continuous function. I can write this. Because phi r is equal to constant. Yes or no? Huh? Yes or no? Phi r equal to constant for all r, for r positive for which this happens. Now you take the limit r tending to 0, then it will be a constant. I name it as a phi r. Is that clear? Phi r equal to limit s tends to 0, because I don't know what is happened at s equal to 0, but I can write this because phi is a constant, and phi is a continuous function. I can write this. Agreed?
Yes.
All of you? All of you? Navneet, Meenakshi, Annu, Ekansh, Shammi, all of you?
Yes, sir.
Phi r is equal to limit s tending to 0 phi s. Clear? Phi is a constant, so I can write this. For any r, you can fix some r on the let's. Hello? Are you able to hear me?
Yes.
Okay. So phi is constant, so I can write phi r for some r, fix some r is equal to limit s tending to 0 phi s. Am I right? I can do this, right?
Yes.
Okay. Now let us check what is phi s. Okay. We are almost there. What is phi s? Our definition: 1 by sigma del b 0 1. You just check. This is our definition, right? Sn minus 1 u of x plus sz d sigma z. Okay. This is I write down this is a wn minus 1. is a constant Wn minus. I am writing this. Clear? Just minus plus ux. Plus ux is a constant. Ux. Clear? Yes or no? Plus ux. Because wn this is 1, right? D sigma, this is wn minus 1, this cancels out 1. Okay. Now what I can do? Now you just see the points. X plus sz minus x. This is nothing but sz. And mod z is 1. That is mod s into mod s is s because I am taking s positive. That is s. Okay. Now you tell me I can choose s to be very small, right? Since u is C2, in particular u is continuous, because I want this to be 0, because I want to write this is u phi s ux, right? So this is the point, u of x minus x minus x. Then u of x plus sz minus ux is less than epsilon whenever s is less than delta. Clear? By continuity. If I choose s very small, then I can make u of x plus sz minus ux less than epsilon. I can do that, right? Because the distance between these 2 points, x and x plus sz is nothing but s. So if I make s arbitrarily small, because s is positive. S is positive. So for some s positive it sits inside the domain, then for any s small it will be definitely inside the domain. So I have taken s to be very small so that so for any epsilon I can always find a delta such that whenever s is less than delta we have this less than epsilon. Is that clear? Yes or no?
Yes.
Okay. So now I use this. You choose a epsilon for any epsilon. This integral w by n minus 1 sn minus 1 u of x plus sz minus ux d sigma z modulus is less than epsilon whenever s is less than delta. Okay. So what we have? We have phi s is less than epsilon plus ux whenever corresponding to any epsilon, for any arbitrary epsilon positive, there is a delta such that phi s is less than phi s is, of course, phi s is always phi s is less than epsilon when s is less than delta, whenever s is less than delta. So just a minute, you just tell me what is phi s is positive or a negative function? Oh, phi is a constant, so nothing matters. Yeah. Okay. So this we have. You take modulus. Sorry. Modulus of phi s is less than epsilon plus ux whenever s is less than equal to delta. Yes or no? Yes or no?
Yes.
Again it goes out. Hello? Hello, can you hear me?
Yes, sir.
Oh, in the IIT there is a switch power off. Just a minute. Okay. Just a minute. Hello? So there is a power off and only laptop is working, but the tablet stops working. Just a minute. What happened? Set up again, I think. Just a minute. There is a power off and just wait. I am logging again. Okay. Hello. Just wait. Hello. You can hear me? Hello, students. Can you hear me?
Yes, sir.
Sir.
Huh. Yes. Okay. Sorry for the. Again, some issue has just a minute. What happened? Sorry, my pen is now stop working. What happened, man? But the pen is not working. I think I have to. I don't know what happened. Just wait, okay? Sorry for the inconvenience. It's not working because okay. Sorry, students, I think I have some problem with the Wacom tablet, so it's not working. The pen is not working. Hello, can you hear me? Hello?
Yes, sir, we can hear you.
Sorry, very sorry. My pen is not working. Suddenly, it's the current off and then it's stop working. Sorry, maybe we can join next class, okay? Sorry. Okay. Hello, Atharva, Shammi,
Yes, sir.
Ekant. Sorry, I'm very sorry. All of you, sorry. Suddenly it stops working. I don't know what happened. Okay, I will try to fix it out and next class we will meet, okay? So I was planning to finish this theorem. But now you finish this theorem by your own? At least, please, when you are coming to the next class, please have a look on the proof, okay? Then I will start from exactly from here. Otherwise, it's a long proof. Otherwise, I will miss a lot of time, okay? Is that clear, all of you?
Yes, sir.
Ekansh,
So we can
Ankit.
also directly say that because phi of 0 is nothing but ux and phi
Yes,
is
yes, yes,
constant.
yes. Now everything is there. So u of 0 is ux. Now you immediately will have that limit s tending to 0 of u of s is equal to u of x, right? Once you have u of x, limit s tending to that is equal to phi of r, and you are done. Clear? For all r positive such that b of xr is contained in omega. That now we have to prove the we have proved that u of x equal to the integral over u over the boundary of the ball. Now we have to prove that. Now what we have to show, that this is equal to the integral over the ball, not on the, only on the boundary, also just 3-4 lines. Okay, try to finish it off. Otherwise, I will explain again that part. Is that clear to all of you? Meenakshi, Kritika, Navneet, Annu, is that clear? Govind, Ankit.
Yes, sir.
Okay. Okay. Try to finish. It's almost done. Okay. Okay. So we'll meet in the next class. Okay. Okay. Thank you.